Alrighty, let's see if this thing's working. Whew. So hello everybody, it's been a little while actually. Today will be a pretty short stream. I'm mostly just checking to make sure that everything here still works and that I can do this, and I'll probably start streaming again more heavily after, like, next week. I'm going on a trip again for a few days and then I'll be back. And while my hair is terrible in the green screen, let's see if I can try it back. Alright, so where were we? Oh, that looks awful too, but whatever. Currently staring directly into the sun. This is not so great, but we'll see if I can get going. So, Cabal new build. I have this thing in how it's already in a build state. So I think the thing I want to do today is kind of get folks caught up on the current state of Guanxi, the logic programming framework that I've been building here. And that's probably all I'm going to have time today. Hold on a second here. Eurosen, I do have some questions regarding relational programming. A, can you use staging instead of writing C++ code and escape on that way slow Haskell? B, can you show what we have after we apply Guanxi to our specification? I'm not sure I'm going to get a chance to do too much of B today. There's a small example of Guanxi that George Wilson wrote recently, where he built, I think, kind of a standard, Niels Bohr lives next to Einstein, who lives in the blue house kind of example. As for, can I use staging instead of writing C++ code? Oh, you mean to see, like, should I generate the C++ code from Haskell for things like the... are you referring to the existing DLX code that I already wrote? I'm not quite sure where you're going with that. Yes, you could use staging instead of writing C++ code. I wrote C++ code because it was more direct and there were fewer moving parts. And it was a small enough example. I still need to go back, and I have a sketch of... what I need to do to... I will turn this into something a little more viewable at some point. What I need to do in order to do SIMD-based DLX, but I haven't gotten that done yet. I have a sort program, give a specification to show what Guanxi would generate, and would it be quick heap? Okay, so Guanxi right now doesn't do any code generation. So that's the thing that Guanxi is being built for. So I'm going to use Guanxi inside of some of Coda at some point for doing that. As for whether or not you're going to be able to build a sort routine just from specification, that's currently a little bit out of reach of what is it Parliament? Whatever the thing that Wilbert has. Wilbert will actually be at my house this evening. I don't know if I'll get a chance to stream when he's here. He's the guy who does a lot of the work on Canron. So we're going to talk about, like, the current stuff that I'm doing and what he's doing. Can I talk about how Guanxi is related to Coda? Sure. So the way I'm looking at Coda more and more is that if I have a compiler, we can talk. This is more of a Coda spiel then. If I have a compiler, right now most of the compilers that you work with are completely syntax directed in the way their type theory works. So in an intentional type theory, that's always the truth. Or almost always the truth. Let's see here if I can pull this up on the right computer. Coda. And I got to pull up chat on the right machine so I can paste it in the chat. Twitch. chat so I don't have to keep the whole window open. There we go. So I can now paste the link in the chat. So Coda is a current programming language project, which is not nearly far enough along for how much time I've spent on it. The thing that I'm working with right there is exploring what it would take to build an extensional type theory on top of a type-based theory. This starts to look a lot like liquid Haskell. You have a type theory in which you write the bulk of your thoughts, and so unlike, maybe I should rewind and say what an intentional versus an extensional type theory is. So in every theorem program you probably worked with, like Coq or Agda or Idris, you're working in an intentional type theory. There you have two notions of equality. You have the judgmental equality that's used by the type checker, and then you have the intentional equality that you can express in, or the propositional equality that you can express inside of the language itself. In a extensional type theory, you can promote the propositional equality to the definitional equality. That means that your terms are no longer enough to actually type check them. So what you want to build with your tactics and what have you are typing derivations, the little proof trees that say that this is a valid program instead of a valid term. So if we play with that, now the syntax isn't necessarily enough to tell me everything I needed to type check. So I've got lots of little program synthesis problems along the way of like, hey, find me a typing derivation. I don't care how you do it. It won't change the meaning of your program if I do my job right as a language designer. So that's all well and good. And basically, if you look at New Perl, they kind of start from an untyped lambda calculus and then add the rules of what does it mean to have a typed language on top of that and build the typing judgments from there. Whereas that's not so great if you want a language with actual type classes. So what I'm doing is I'm starting from a language that is strong enough to figure out type class dispatch, and then I'm adding the extensional layer on top of that. This means that I wind up with, for the most part, like the meaning of the program's already set, but all of the laws and things like that are the kinds of things that I'm going to wind up synthesizing code for, either by the sort of liquid Haskell approach of just do it automatically using Z3 as the only tactic, or using a more interesting tactic style, which is what Guanxi is sort of intended to address, is, hey, I need some kind of logic programming framework in which I can write my type checker. And it would be nice if I could then exploit that further in the language by saying, hey, here's a logic variable, go plug in whatever you can do, and then work with the tactic system / Guanxi / what have you to fill in the holes. And that's, I think, a rough sketch of where we're going. Hey V, how you doing? Let's see. So that's roughly what Coda is about. As for how to fit it into Coda, that's an entire work in progress. What I'm using it for right now is to have a language for figuring out how to program with backtracking and references, right? Like how do I even start working? Yeah, but you'll be able to watch it on the video when it gets archived later. So you should be okay. So that's sort of a very rough sketch of why Guanxi is relevant to my interest in Coda. What eventually would be the output? Yeah, I'm not there yet. If you want to see, I have some small logic programming example, or we now have some small logic programming examples in Guanxi. The main thing that Guanxi will be useful for in Coda is writing the type checker directly in it, because then I could, if we're looking at program synthesis, there's a lot of things that try to restrict, like you're generating these big syntax trees, or in this case, typing derivations, and some of it's going to be syntax directed, and some of it's going to be, hey, look, you need a side condition in order to prove this equality, go. So being able to synthesize those directly or use a tactic to search is kind of key. Guanxi isn't entirely about automatic programming. Right now it's basically just a logic programming framework. One of the main purposes that I want to put it to is quote unquote automatic programming, or at least think of it as like the glue to hold together the tactic language for something along those lines. Right now, something like Cameron can handle existential questions. There exists a queue such that eval of q is q, go find me a quine. But that's not so great when you want to be able to handle universal quantifiers in that search. So some of the designs in Guanxi, some of the design decisions in Guanxi are currently kind of at odds with what I want it to do, and I'm trying to figure out whether or not I can get away with what I'm doing, or if I need to refactor things even more aggressively. So I think that kind of segues into a bit of a tour of what the heck we have right now. And yeah, I'm not sure. I think I did something on this maybe last stream. It looks like I thought I did a stream 25 already. Apparently I delayed too long in archiving it and it got thrown away. Maybe I didn't. Alright. Do I have anything other than I just have the one library right now. I started breaking this thing apart, but then wound up not taking the broken apart version of the library. So I did a bit of a tour through what is in Guanxi with some folks on IRC, and I felt that would actually work pretty well as a introduction to, or not an introduction, just a whirlwind tour of what the heck is it that I'm collecting in here, because it's starting to sprawl. So let's see here. If I look at this, I think the main starting point here, we're going to get to like a little toy theory of equality, and what we have is probably something like ref, and then we'll backtrack to see whatever we need to. Do I plan to show my approach in the Approaching ICFP Mini Cameron workshop? I have not talked to Will or anybody about doing so. That's possible. When he's here tonight, I might ask him. So let's see here. So ref is built entirely on built-in types. So there's a old paper by Guanxi. References. Actually, I've got the link right here. Set mouse equals, there, I can grab it. Let's get out of it. Usable. So is this, nope, that's the wrong paper. Do I have a reference to my references? No. Find the paper, please. Type logic variables in Haskell. There it is. So, Guanxi and Peter Lungloff. I'll dump this into chat. And this is, I actually implemented this technique before I went back and read the paper, but it turns out that they implement this thing as like their second or third example of, in their case, how to embed Prolog into Haskell. Gee, it seems somewhat familiar. The idea is the same, which is that we'll build a monad for working with references, which will actually be IORef style references. The difference is that when you go to, but we also want a non-determinism layer, so we're basically looking in list T of IO or something. How do you work with IO refs inside of that? Well, when you go to backtrack, undo whatever change you made to the reference. And I think they've got the write reference reads from, let me scroll this thing up. To write to one of these references, they first read from it, then they write to it, they call the continuation, then they write back whatever was already in there, and then they carry on. So that's what the ref module that I have here implements. It provides a version of what they call an LP ref. Using this unwind primitive, we built this on stream a little while back. This was when we switched Guanxi from a Canron style search order to a depth first search model, so it fits more closely with SMT literature and the like. So now you've got references I can read and write for them, and this is kind of the workhorse that I use to build all the propagator machinery that lives inside of Guanxi. And then there's another workhorse that gets used a lot, which is this notion of a coercible key. And this is based on a paper by Etsy vendor plug and Guanxi, a couple others, or I guess it's Pablo Perez. Okay, I don't know him, but the idea of a key is what we want is a monad in which you can construct a new key, test keys for equality, and this sort of, it's used in a lot of the places where you would otherwise pick up a typable constraint, but a lot of the things that I'm going to be working with couldn't be typable, because if you use the ST trick, which is what this for all S key MSA thing, and you have a type variable S is not going to be typable. And I'll dump this link in chat. Sorry. There you go. And so using typable all over Guanxi is a bit of a non-starter. So I wind up having to use this key construction. Whenever I need to build a heterogeneous map, what I can do is I can allocate a fresh key, and then I can create a I can just make a key, make a reference type or something like that acts as, okay, fine, you've got a map in my environment, and in the environment I'm going to store a box which has the key that you need to unlock it and a value. And I use this pattern over and over again whenever I need to actually, whenever I can't just get away with a depth first story. So keys pop up all over the place inside of the Guanxi code, but they're a really painfully simple concept. You can see the whole module here on the screen. Keys are mute vars, which are the data primitive version of a stref/ioref. We have coercion of keys, which is the only unsafe bit of the API. This really belongs inside of base as an instance on stref. This one is safe. I went to propose one that would also add the, but I didn't realize that strefs were coercible in their last argument, or representational in their last argument. So this one is sound because it only uses representability of the A in key MA. And in theory, this should be a key SA, but then the code gets really repetitive. So right now I'm getting away with M's. So we can create a key, create a box from the key, unlock the box. And this will pop up over and over again. Another thing that I use a lot are a bunch of data structures from purely functional data structures, slightly modified, also using a trick from Etsy vendor plug. So that's what all this aligned sequence stuff is, but let's just look at unaligned sequences. So here we have a bunch of machinery for like ad hoc things that I can check for nil, const, unconst, snock, build a singleton version of, and reversed versions of those containers that flip in the other direction, and in some instances for default data types. I want all of these operations to be O1, so if there isn't an O1 implementation, I just don't provide it. And then I can build queues using an Okasaki style queue. And then build O1 catnable lists. So cat is a list type. If you use nil, const, etc., it works just like list, except all the operations are O1. You know, the appending of two lists is O1. It's like a difference list in that respect, except for the fact that also accessing the head is O1, which is not the case on a difference list. So I have this code line here, and I use it a bunch. And then I have similar things for aligned code, where this is the stuff from Reflection Without Remorse, where now these things have like a type index to build a funny free category. So now nil builds things where the indexes are the same. Const takes something from unconst, constructs one of these views from A to B, but there's an intermediate variable. Singleton builds one. Snock. These things compose A to B, C to D, like dot. Or A to B, B to C. And then I provide smart patterns for constructing and deconstructing these things. And rev gets uglier because now it has to flip the indices, and et cetera, et cetera, et cetera. So thrist replaces list in the previous code, and we get queues and catnable lists, but now they're catnable. This is like building a free category with all of the operations for append and get the first like little arrow out of this composed sequence of arrows in O1. And I use this a lot more later. So if we look in aligned, I think the main thing that is interesting here is the implementation of the free monad using the Reflection Without Remorse encoding of the free monad. I won't go into detail about why this thing works. There's the paper by Atsi on this on Reflection Without Remorse. First of all, there's the code that he has, which I did not use directly for various reasons. And then this paper. So in this paper, he goes through and kind of proved to Oleg and then to the rest of the world that it was possible to implement free monads with like sort of an O1 bind and an O1 inspect the outermost constructor. Whereas previously we'd used codensity in order to get the O1 bind at the expense of converting back and forth into codensity. Had to walk the whole tree. So I'm going to use the Reflection Without Remorse trick a few times inside of this code. One is, in this case, just once inside of the free monad code here. And then inside of here, there's a little unification engine that uses the references that we've already built. So this lets you take, if V is like ref M, maybe free FM or something like that, or free FV, like if you had a new type here, then this lets you take a variable and a free monad and get out the free monad that has like had the unification variables flattened out. This lets you unify two free terms, and then Zonk takes one of these things with variables inside of it and then smushes all the variables out. Hi, Emily. So that's what the aligned free stuff is. It's just an attempt to build a slightly cheaper free monad if I'm going to be dealing with building syntax trees maybe I should be building them in something that is a little cheaper for the operations I'm going to perform. Not sure that's going to pay out. The aligned sequence stuff also gets used inside of some other delcont monad prompt things later. So I was playing with ways to like capture the current continuation in my code, so I built a version of, there's a CC delcont, I think is the name of the library. And it provides some operations that look a lot like this. You've got the ability to create prompts, push a prompt, and then like given a prompt, go capture the the continuation since that prompt, or something to do with with that continuation, etc. And then they build various control effects, shift and call CC and abort and all this kind of stuff. So I went and supplied my own kind of version of it, but instead of building it on trust like the existing code, I build it on top of the reflection without remorse technique. So again, type align sequences pop up over and over again. Here they are Kleisli arrows in this CC monad, and this is awful code, but the whole thing results in an instance of that monad delimited continuation library or class. So inside of here, you have delimited continuations built on top of type align sequences. I don't have much using it right now. I've got an example, I think, like using like iterators, I think from the original delcont paper, where you construct this notion of an iterator, which is here's an answer and a some monadic computation that gets you another iterator, which is either we're done. It's like a off by one list T, where we don't have the outermost monadic effect. And like here, you can feed this thing like an operation like using for from data.traversable, for something, and it will construct an iterator that will walk over that using the delimited continuation machinery that we have in monad prompt. I think George pulled it out into, I had code in there. Prompt iterators spec, there it is. Yeah. So here we can construct an example, which is, hey, there's an iterator, we'll use for from 1 to 5, and then say that we're done. So here's the final what to do in the end, and repeatedly loop constructing an iterator. So the prompt stuff I think is largely irrelevant, other than the fact that it happens to use the delimited continuation stuff. And I had a couple of use cases that I'd hoped for it. What else is in here that is of kind of general interest? So we have the aligned sequence and the unaligned sequences. I also have these relative sequences, which uses the same trick that I use in the rest of Coda, where in Coda I have a bunch of the stuff parameterized on an arbitrary group. So there's something for group relative code. Here I'm fixing the group to be these funny little affine transformations. But it's basically the same thing where you're allowed to apply an affine transformation to the elements. But these affine transformations are kind of funny. So what I'm using is this transformation of ax plus b, where a and b are drawn from some ring. And so if you had like f of x equal this thing, and you had g of x equals cx plus d, then f of g of, let's just do f of g of x to be clearer. This is a times cx plus d plus b, which has the right form, acx plus ad plus b. These become coefficient of x. This becomes the coefficient, the second coefficient. So there's a composition here. But we can also construct an inverse if A has an inverse. So if I limit A to being one of the quote-unquote units of the ring, I have an inverse for this notion of an affine transformation. So if we look at, like, say, the ring that we're going to work with is going to be the integers. The units are which integers have integer inverses that are integers. And the only two are 1 and -1. So this is going to be like either, x plus some delta or minus x plus some delta. These will be the two forms that we're allowed. And any equation of this form has an inverse. So if y equals x plus d, or y equals this, then I can compute x as a formula of y, which is also of this form. Yeah, I think I've got it down here. Yep, b over a, there's my b over a, and I've got y over... Yep. So the idea is this lets this be a group, which then lets me apply all of my group relative tricks from the Coda code base. I gave a talk on how, why group relative structures are interesting, I guess, on monoidal parsing. I'll just dump the link here. I know I've included this in the chat a couple of times in previous streams, but just to keep things self-contained. I don't recommend watching it now, but it does go into the group relative construction that I'm using here and some semi-direct product stuff that will be useful later on. So here we've got one of these, we've got these affine transformations now as a group, and I've got a action of one of these affine transformations on A. And then everything else here looks just like the unaligned sequence without the, here we've got nil, cons, all the classes that I had before. We have queues, we have catenable sequences of things, except for the fact that now I can relocate an entire catenable sequence in O1 after acting on it with an affine transformation. So if we go into domain here, there's interval. Inside this internal module. And this code is awful right now. But the idea of it is to implement interval arithmetic using sort of bespoke propagators and this notion of a group acting on my intervals. So what I have are sort of reactive intervals. What we can do is we create an interval, and then the interval uses a form of UnionFind to find the sort of root copy of the interval. But that UnionFind has been modified so that at every pointer to the parent, there's a group that acts on the result of whatever the parent is that you find. The group is one of these affine transformations. So let's motivate it. Let's say I have x equals 1 to 5. And I just want to learn that y, y is actually equal to x plus 5 or something like that. I could build just y as an interval constraint here, and then prove that x equals y plus 5 or y equals x plus 5. But then I'm going to enumerate x and y separately, and what I want to do is have the information from x actually propagate directly into y. What I call eqref. So eqref is saying that this reference is this affine transformation applied to this reference, or this this interval. C. This is using the guts of the thing. So I've got a, where is it? It's hiding down here. It's hiding down here. Yeah, this interval is equal to that interval, but then you have the ability to relocate an interval in O1. So here we've got like, the workhorse of this is that I have some reference to content, and content is, it's hard to find. We're either at the root, in which case we have all the information about a root, or we're a child of the root and we have an affine transformation that we're going to apply to whatever result we get. And then given one of these contents, I can shift it with an affine transformation by applying it to the child here, or relocating the root directly. And an interval is either, I'm an actual concrete integer, or I am an interval, which is an affine transformation and one of these references to, well, is it a root or a child? Chain until you get to the root. So it's a modified form of UnionFind, tweaked with this group acting on the paths. And I need a group rather than just a monoid, because I could have paths with a monoid on them, getting to some root value, but to get the nice asymptotics of UnionFind, you want to be able to link, like, given two elements that you want to say these are the same thing, union x and y, I need to be able to like make x a child of y, or I need to make y a child of x, and that means that I need an inverse for the thing that I'm going to have that acts on this relationship between them. So I wrote this, I think, before the last stream or after the last stream. I'm not quite sure where I should probably have watched some of my last stream. And the idea here is, while the internals of this thing are god-awful, from the outside, the user works with, hey, I've got an integer and an interval, and I'm going to say this interval is greater than this integer. That just shrinks the interval. That would work like a normal interval library. Or, this interval is equal to this, or greater than this, or etc. I've got a funny one where it's not equal to. And here's where we're sort of working with intervals inside of a non-determinism monad. So what I can do is, well, we're either greater than it, or we're less than it. Like if we're going to say not equal, like I can just special case the one thing. I've got the ability to create like a propagator that says, hey, the moment this interval has a lower bound that isn't minus infinity, run this code. Or the moment this interval has a upper bound that isn't positive infinity, run this code. Or, hey, whenever the lower bound, or on high in the upper bound case, whenever that bound changes, tell me to propagate, so I can propagate that information around. And you should always use a valid propagator here. These are sort of like propagator command, like callback hooks. Tell me the changes since the last time I fired a language specification of Guanxi. No, I don't have one. Right now I'm building an EDSL, and it will keep growing until it's able to express all my problems. So once I've got these like sort of what is, once known as a propagator that will fire only once you're reduced to a concrete value. Specification of the EDSL. The EDSL is the thing that I'm kind of walking through right now. It's a library. It's got a whole bunch of individual primitives that build up. It's very operational, as Emily put it. So here I can like say, hey, this interval is the this interval is the signum of that interval, and it'll like push information back and forth if they're concrete. And like once you learn some bound on the signum, we can play games with like propagating information back to the other thing and vice versa. Absolute values propagate. And here's where I actually needed the ability to negate things. And that's why I needed that affine transformation thing to allow for -1. Because I had originally only allowed for equating two things and then like shifting them a bit. But then if I want A equals the negation of B, then I would have to use like a propagator to push information from A to B, and it was really expensive. Do I use finally tagless? I'm working in in monad ref. So any code that you write in monad ref is Guanxi code. Well, actually, there's some refinements to this class later on. The application to a concrete. So concrete. How to put this? So concrete lets me build an like take an interval and try to refine it until it is a actual integer, right? So I've got an interval from 50 to 100 or something like that. And what this will do is every time you go to refine it, it will try and carve my interval in half repeatedly, propagating that information to everything that's listening, and then hopefully that will make everybody who's listening go away before I have to get down to a grounded interval. But if you used concrete, it's just going to keep refining until we're done. Until you've got an actual interval, an integer. Refine is used inside of the callback at the end to make sure that everything's grounded. So I don't know if that answers your answer or your question, Christopher. So constructing an interval, if you know both the lower and upper bound and they're both the exact same thing, then you've got a concrete interval. Otherwise, if the interval is impossible, we blow up the world. Like that's the benefit of working with intervals in a non-determinism monad. And then we check to see when we go to ground, which is what we do is I run my I build this thing as sort of an Overton style finite domain solver. So what it does is you in your monad you're accumulating a bunch of constraints on what the world's going to look like. Those are going to be your propagators. And you do some non-determinism stuff as you go. And then when we're done, what I do is I fire everybody's finalizers, basically. I pick somebody and say, okay, you do something, because I need to actually get down to concrete values. And it'll like enumerate over the cases that are left. And when it does so, that information propagates to the other variables and like hopefully reduces more other cases. When I'm dealing with these intervals, instead of going down to an actual integer value, I use the ability to refine the interval to like an interval of half the size. And then I keep doing this over and over again, but only while there's somebody who would propagate that information. And that's the key to making this thing go. So if nobody's looking, I don't bother to refine you. If no one can blow up the universe if you became a different value, then it doesn't matter what value you have. And then I have some things in the code here for tracking the multiplicity of a solution. So like if you would just give back the same answer for 5 to 10, then I'll tell you about there's 6 copies of that answer. And that's what this thing's tracking. Or if you're going to give the same thing from minus infinity to positive infinity, and you cared about like, well, how many solutions are there? I'll tell you there's infinite many of them. There's infinite many copies of this thing, Aleph, not, or whatever. So bottom construction interval from minus infinity to infinity. And then when we go to wire up intervals, I think the thing that makes this thing different than the usual interval story is that given 2 intervals, if I say that this interval is less than that interval, what this will do is as you refine one of those intervals, it will actually refine the other. So these aren't like, dead bits of interval code. Now, in theory, I've got to change some stuff about the propagators to enable me to clear out propagators that cannot push any more information around. And that will matter to, like this, if I can fix this to do, then this grounding check becomes more reliable. Because it actually becomes more useful. Because this would then narrow the interval until nobody's listening, or nobody can propagate any extra information from it, including these LE, etc. operations, which would be the poster child for this. And then, yeah, so this is basically the interval code that I have right now. Earlier on the stream, I've talked about sort of this tower of adjunctions that I'm playing with, where we can start with like a concrete domain, and then we can move to an interval domain, and then we can move to octagons, and then we can move to polyhedral domains, and further on into Presburger arithmetic and what have you. So this is sort of the first step along that way. And the propagators, which is something I learned along the way, the propagators sort of let me borrow the power of things further to the right of me in this chain. You know, like we're moving into more and more complex domains, but with the cost of accuracy, right? So like you can do most of your computations with just intervals, but then like you've got like an LE constraint or something like that, where you like whenever this interval changes, you're going to push some information into the other one. It's not as good as the polyhedral domain or something like that, where we could actually build a big linear equation inside of here and then push all the information around with these intervals. But we're not going to delete inaccessible or unuseful constraints as well while we are in this interval domain, for instance. Similarly, in the octagon domain, you could use a propagator to kind of push around a polyhedral style constraint with full fidelity, but you're not going to be able to get rid of it, which is this step here, as accurately as you could in the polyhedral domain. So that's the thing that I'm kind of starting to see, is that playing with this sort of tower of adjunctions of different abstract domains with propagators on top. The propagators let me kind of like dip a toe into a deeper domain, but retain, at the cost of accuracy in terms of what I can express. So the next step up here, I think, is to like get octagons into this code. And that's going to require another modified UnionFind with a slightly different trick. And so it won't be a UnionFind with a group. It'll be a UnionFind with like a shift, which acts more like a semi-direct product. I'll have to play with that. So I wrote this code, and I believe George Wilson wrote a ton of tests on it. So that's the domain stuff that we have. So that's sort of the workhorse of using the reference machinery and supplying like kind of bespoke propagator logic. I have a actual library of the signals module, which provides sort of just generic propagators, but it hasn't proven very useful, I admit. I've kind of, it supplies me the multiplicity code that I was using in there. And it supplies me with the ability to create propagators and fire the propagators. But then when I was building intervals, I wound up having to build my own notion of a propagator. And part of it was these propagators care about telling me when I change a value. And so I wound up having to build like a catenable list of these propagators, such that I could relocate a propagator. Because if I'm listening to an interval from 1 to 5 and somebody tells me, oh, that interval is actually the same as this other interval from, I don't know, 30 to 33 minus 30, I don't want to be notified about values like at position 30. I want to be notified about values between 1 and 5 with anybody who's listening to it. In theory, that actually works already, Manip. You can do the barometer test. I don't know if... I think George was writing me some examples. I don't know if he actually got that one in yet. But that's the sort of thing that you can do with this now. And it's more directly accurate in some ways than the code in Alexi's thesis in that regard, because here we'll actually enumerate the cases, which will cause us to actually check the answers, whereas he sort of is able to narrow the answer, like the answers within this range, but he's not tight on the bounds. This will get you tight bounds. I think for ICFP or for Lambda Gem, George should have a for one of the examples in the talk he wants to give. He should have a worked version of that and some others as examples. Let's see. So we've gone through why the aligned stuff and relative and unaligned stuff exists. We've gone through key. We've gone through ref. Let's see. What else is in here that is interesting? The domain stuff was probably the most interesting bit so far. I've got a little crappy theory of like disjoint sets. Like I probably should have done this before doing intervals. Where here you have the ability to create disjoint variables. So you create one of these things with a new variable, and then you're allowed to union them together and then assert whether or not two things are equal. This eq is actually you can union them and then find the root. And this should eventually pick up an API that looks like this equality thing, where here you're allowed to create new terms, say this term is the same as that term or isn't the same as that term, and then you can decide whether or not they're the same. This is the correct API for what that disjoint thing should have. So find shouldn't be in the public version of the API, but is and isn't should. So you can create like 3 variables and then say, well, this is equal to that, or this one, or this is equal to that, and using is and isn't, and decide. You can answer these. It'll give you back these answers, and it'll do so consistently. It'll say, oh well, okay, x equals y. Okay, yes, or no, if it's not constrained to be true or false. So it's like a toy theory of equality. But then I have to add congruence closure to it, and then I'll have like term equality. Is there a permutation combinator right now? I don't think so. So that should be able to be built using the sharing machinery that I have. So this is based on this paper from Sebastian Fischer that we built on stream, I think, a few months ago. Set mouse equals. Grab the link, paste it in the chat. So he has this library. And the code in here is based on the original paper, not the current explicit sharing library that is on Hackage, mainly because I can't fit it into the rest of the things that I'm doing with Guanxi if I take the current approach that's in the library that's on Hackage. So in theory with this, one should be able to do permutations of like a list with sharing using one of the examples from the paper. And so the idea would be to say, hey, look, I want to implement sort. Give me a constraint. Like, what does it mean to be sorted? You give me a sort that just tries all permutations and then runs through the list. And it would actually be almost efficient. Like to implement sort from a specification. So I think Erosin or somebody was like saying, what would a sort look like generated by Guanxi? Well, I don't know that Guanxi currently isn't smart enough to do the program synthesis for a sort routine. But that would actually be, well, how would you sort? It's not as bad as you think because it actually does this functional sharing trick. So that's in the original Sebastian Fischer explicit sharing library. As for permutation stuff, so what I want to do is, for that, it's much more efficient to implement all different constraints. More efficient. So I want to explicit all different propagators rather than guessing permutations. So like that would be how I would handle Sudoku if I needed to do it today. The other thing you can do for Sudoku is you can just feed it to the DLX machinery that's in here. So right now DLX is only naive. I don't. What is that sort? It's like, it's none of those things. It's like find me a permutation of the elements that is in order. Does that have a name? Like it's like logic programming its way through the constraints that it would have, and then rejecting the worlds in which they're out of order. It's like a quantum BOGO sort. So yeah, so in theory right now the machinery for implementing Sudoku would probably be to feed it to this cover machinery. Like the Queen's Code. Quantum BOGO sort is pick a random permutation and then blow up the universe if the thing is not sorted. And then if you're in a universe that survives this process, you have a sorted list. It's an old joke sorting routine. So I think that's most of what we've got in Guanxi right now. So I think the next step would be I want to get some more machinery for doing unification, more machinery for doing yeah, so I want to get the machinery for doing unification, and then we're starting to get enough stuff to be able to do the logic programming things I need. I do have one more like work in progress thing, which is, how to put it? So there's a paper on something called neural canron, which the folks who are working on canron have been doing. And with neural canron, what they're doing is like saying, hey, look, we have some probability distribution of like symbols that actually seem to show up in the actual programs that the programmers write. How would I want to synthesize programs using those terms, but I want to synthesize things with like the right distribution so that the code that I produce like actually looks like a human who could have written it. And so they want to sort of weight the branches of the probability space that they walk through using these, like they start with some like n-gram, like bigram models or something like that. Like, what are the odds of seeing an if inside of a lambda? And the current canron approach for doing that, I think, or whichever branch of canron that's in, it ascribes like the highest probability one gets the first slot, and the next one, etc., and so on and so forth down. The problem that I have with this approach is that the KL divergence between the probability distribution that they want and the probability distribution that they're encoding it with is quite high. Because like the first thing in their list gets half their time, and then like the next one gets half of that, etc. So if you don't have this exponential fall off in your probability distribution, then the naive sort of bigram model doesn't work so well. So my first thought there, and I think I've talked about this on stream here before. This is going to be largely a catch-up session for folks who haven't been watching, because I can understand that watching 30 hours worth of earlier Guanxi stuff is probably not something I can expect of everybody. How do I synthesize things with like something closer to that true distribution? And so one observation is if I were to use something like an arithmetic code, I can use like fractional decision bits, or let's just like first just do a Huffman code. I could like Huffman code my probability tree, and then I'll get a tree of bits basically to get to an actual decisions. Now weighted at least by powers of 2. But if my probability is like 99% or something like that, Huffman's bad at making use of that information. Like it can't get past 50%. So now we could start looking at using something like an arithmetic code rather than a Huffman code to encode my decisions. And then the OR in my monad, like, you know, the less than pipe greater than, is like flip a fair bit. And I can provide a choice combinator that says, okay, choice these things with these probabilities, and then consume bits worth of information using an arithmetic code. So the idea would be to use the decoder of an arithmetic coder on sort of random bits. So like if we were to just sample what I could do is I could say, okay, whenever I encounter an or, try the left or the right side, flip a coin, pick one side, and go down the thing. But if I encounter one of these choice things, what I'm going to do is like use up like state in my arithmetic code of like in my choice space. So I have some problems with this. One is arithmetic coding is relatively slow, so I could use asymmetrical number systems. So rands and tans, the stuff that Jarek Duda has been doing. That's another viable way to do this. The other problem is that arithmetic codes tend to have like little corrections applied to them to avoid like small intervals that happen to directly straddle the midpoint, and that kind of destroys some of the distribution properties that I would want to just be able to feed this thing random bits and decode them. So I haven't figured out how to nicely fix up that part. So the thing that kind of expands the arithmetic code in order to make it efficiently implementable kind of ruins some of the distribution properties that I would like. Now, how much does it ruin them by? It's not that bad. In theory, I could just continue on with like the random decoding step. Like the KL divergence between that plus some extra redundant codes is probably way smaller, but it does mean I might repeat some answers. Another thing is that like, how do I use this for synthesis if I'm like kind of exploring this tree worth of bits like by sampling? So one thought is to kind of keep track of the tree worth of bits that I've explored is like literally a data structure. And then whenever I've kind of like fully exhausted some portion of the space, like, and I have a decision that would keep me like send me in a direction I've already sent, just always take the other option. And I can keep doing this until that tree of bits collapses to say, hey, I've explored the entire space. There's some complications, like with a Huffman code, everything is an integral number of bits. With a arithmetic code, you wind up with, oh, well, this thing is actually the interval from 0 to 2/3. So if you went left, you covered this thing, but you also covered like part of the other bit. So when I go to like build this memoizing tree of what have I explored, I also have to fill in, oh yeah, and everything to the left of, you know, the top end of this interval is also taken on the other side. So I have to build that thing. And that tree, this is sort of the cost of doing a depth first model with sort of random restarts, rather than using the the sort of like explore everything with this funny non-depth first, non-breadth first search that Canron uses. I have to keep the tree around, which is my leak, whereas in Canron they have to keep the like frontier worth of continuations around. So I'm still thinking this is largely a wash. It seems to be somewhat in favor of my approach, and the nice thing about my approach is that it like integrates nicely with all of the existing SMT solver stuff. So the things I need to get back to doing here, I need to get back into working on abstract conflict directed clause learning, and integrate that into my my monad here, and I need to get some more work on this stuff. Do I think it's feasible to develop automatic programming? I think it's already feasible for small examples, and that's okay. Like, I don't need to use this to synthesize big things. I want to synthesize small fragments of code scattered across a larger code base. So Nadia Polikarpova has some interesting work on something she calls synquid, where she uses liquid types and then synthesizes lots of little examples inside of other things. And I think one of her examples is really compelling, where she gives a declarative specification of, hey, in order to call, like, I don't know, she gives like a CRP or something like that for a conference, and says, okay, well, like the end user should not be able to observe the differences between these states, and then gives this like small declarative specification of the security thing, and then uses the sort of automatic programming thing, as you like to refer to it, to generate the checks around those calls using the sort of liquid Haskell-ish types. I think that's really compelling. I also really like The stuff that Resin and like Edwin Brady's stuff for Idris 2, where they're using resource constraints like kind of like linear Haskell, the linear types and Haskell stuff, to help constrain the syntax trees more. Like, hey, like resource utilization helps you find the right program. It's effective at pruning trees. I think the liquid types are effective at helping you prune trees, as Nadia Polikarpova has shown. I think those kinds of things, like I want as many things as I can possibly give me to help prune the space down. And I think if I'm willing to throw enough machines at it, I can help attack the exponent to handle some of the extra problems that I have on quantifiers. So this is sort of the general space that I'm heading in. I'm not looking to do it in bulk in production. I'm looking to use it in like small pieces of production, and I'm looking to use it fairly heavily if I'm going to do this this sort of extensional programming thing with like mostly syntax derived things, but with the occasional side condition that I want to kick out of band in Coda. And now I can see the fact that my green screen doesn't quite cover my... There, I guess. There. Wake up, computer. I've been rambling too long. So yes, I have some hope there. Oh, I gotta click on the right machine. At least that's a sketch of my thoughts. How long have we been streaming? We've been streaming for about a little over an hour. Anything else here that's really worth kind of taking a tour through? There's not much else here. Domain, we've gone through that thing, like the basic concept of group. The logging stuff isn't really relevant to current conversation. I think this might be, can I say a blurb about the key monad? So I don't use the key monad per se. What I use is I use anything that has, like I used to use monad st or prim monad as my key monad. I create a new mute var. I just have a mute var that holds onto a proxy. So when you create a mute var, that mute var, like if you had two keys, comparing those keys for equality, like is telling me, okay, well I had the same type at the time this thing was created. And then these values kind of plumbed around through memory and then came back together later. So it should be valid for me to coerce, because the only thing I can do to a mute var is coerce its argument here, or use read and write mute var. But proxy only has one value. So the A stays alone, or stays intact, like the type A. So this coercion is at least morally justified. So we create one of these things, create a value that like gets plumbed around in memory that you're allowed to use to, if you had a key MA and a key MB, you can then like relearn that they were the same thing. So I use this to recover type information. I use it in that prompt code that I mentioned briefly. So like way down here, there's a bunch of stuff that uses... This uses a stronger version of it because it's not based on coercible. It's using test equality. This is using like key, not key.coercible. And here what I'm doing is like recovering type information about the thing in the middle. I've got a key for the thing I'm looking for, and this split tells me the damn type that goes in the middle of this thing. Whereas in the CC delcont code, this thing is unsafe. It's just, yeah, trust me. Why do I like propagators? I think they're a good sort of general purpose tool for non-deterministic, eventually consistent, etc. style code. It gives me a lot of freedom about how to implement this glue. So like like the moment I say, oh, that thing fits into the propagator like theory, I can just like throw it into Guanxi and run with it. Like I don't have to worry about it anymore. So that's sort of like where or why propagators have been kind of like at least a guiding tool for like how to think about this stuff for me. Oh, I didn't actually show a couple. There's a couple more things in here. One is like, so there's this FD monad, which is like a finite domain solving monad, and it's like this par monad, which I haven't introduced my version of par, but reader T with some signal environment of logic T of ST. So this ST gives me mute vars, even though it's not really safe to use them in the larger comp T thing. But then I can use them in order to build keys, and living on top of ST, this whole thing is in monad prim, and I can use my refs inside of here. And the signal environment is like all the information about like what finalizers do I have to call at the end of this whole thing in order to make sure that I'm actually got a grounded term. And then this par thing will let me do some other more LVAR-ish stuff later. And then anything in this FD monad can be run, and I can produce answers that also include the multiplicity of, like, hey, there's 6 copies of this answer, or if this is nothing, there's an infinite many of them. And I did mention par briefly. So I have this par monad par class, which gives me the ability to fork, halt, and yield, as well as capture the current continuation for a single use, not for multiple use, safely. And having monad cont as a superclass is a bit of a lie, but I should play with that later. The idea here is that I want something that works like Lindsay Cooper's par monad, where you can, in her world, you can fork and you can read and write to version variables, but like, or not version variables, to LVARs, but your reads are only allowed to be threshold reads. So everything that I have, like my intervals and stuff like that, the code that users should be able to write morally are threshold reads. And so I have some additional propagators that do some non-threshold operations for pushing information around between intervals. But that, like, users should be able to write threshold reads, or if they do a real read, like, hey, get me the concrete value of it, they are non-determinism down to the point where that's safe again. Like, the non-determinism is where I'm grounding that out. So it's par plus non-determinism, but but that means that whenever I have an or, a monadic pipe, less than pipe, greater than m plus, I have to copy the entire universe, including all of the people who are non-deterministically running in that universe, right? But then empty blows up the universe, including all the other people. So I can't use empty as my way to stop. So halt is, hey, this thread that is running in this universe isn't going to do anything more, but don't blow up the universe just because I stopped. And then yield lets me do cooperative sharing, or cooperative threading, like within universes. So the idea is the par monad that I have is sort of like it's really a concurrency thing, not a parallelism thing. It's a concurrency thing within a universe. And then non-determinism on top of that is basically, okay, we've copied the universe to make some decision, including this entire system. And one of the things I can do with that is I can build futures and promises. Let me go to promises. I think I've shown this already on the stream. But a promise has a reference that holds on to a maybe value and a signal that I can use to like wake everybody up. And hello to Neb, and it is very nice to be streaming again. So you can create a new promise. You can fulfill the promise by telling it its value. And you can demand the value of a promise. But if you go to demand the value of a promise and it's currently unfulfilled, I have to like block waiting for that promise to be fulfilled. And so what it does is it captures the current continuation of what you want to do, attaches what you want to do as a propagator to the promise, so that when that promise is fulfilled, your current continuation will run. And then once it's done, that extra bit of code then halts. So now we have fulfill and demand. So fulfilling a promise just fires the propagator and blows up the universe if the thing has already been fulfilled with a different answer. And so that gives an LVAR style. Rosen, I don't know how I would do it otherwise. So the capturing of the current continuation, I need some ability to like have multiple threads worth of code, but also be able to have non-determinism. So this was like a way to get everything to work together. So like there's a whole bunch of other logic code like waiting to happen, like further downstream in the monad, and that's the continuation. I mean, it's linear per per copy of the universe, I guess. It's really hard to explain. So once I've got promises, I can now build futures. So a future is, hey, there's a promise, and I will fork, doing the operation and fulfill. And I can block until the future is fulfilled. So this like lets me like pretend I'm working in a concurrency kind of setting or like a parallelism setting. I can work with futures and promises inside of the code that I have for dealing with propagators. So the propagators can like wake up and push information around that way. So we can work in either style, kind of an inside out or an outside in style, where you work with explicit propagators or we block waiting for something to change. And in theory, I could do the same thing. So like this promise style code, I could change demand or something like that. I could do more things in this style in the interval code, and I haven't done that yet. Concurrent, so sequential processes. Yeah, in theory, like, so I'm not happy with this par story in some ways. Like, I really do want to rename it to Conk or something. Because there is another parallelism story, which is that if I do that, let's use the arithmetic coder in order to like explore like trees with the right probability distribution. There's a parallelism story on that where I build the outer tree in parallel. And then this concurrency story is sort of within a solution, like, or within a universe doing more things. So I think this is a good place to break. We've kind of done the recap. And I'm going to be off for a workshop for Miri for the next week. And I come back next Wednesday or so. And I'm around, I think, the whole next month. So I should be able to get some streaming in this month. I was out of the country for like pretty much the whole last month. And some stuff before that, etc. So we should be able to get back into this, and now we've had at least a relatively short catch-up session that I can hope to send people to on where the hell are we and why are we in the same basket. All right, I hope that was useful for folks, and I will see you next time.